What is it? What's going on?
I'm trying to organize the study group, sorry.
Okay, do that later. 8 o'clock, and everything. All right. Other comments or questions? All right. Let me talk about, some of the things you want to make sure you are able to do on the test next week. This is like a review session, I guess. Obviously, you're going to have to name compounds, okay? And just like you did in the last test, these compounds will not be just alkanes. You will have attached to the carbons halogens. And so if you have a chlorine, bromine, fluorine, iodide, then you want to use those names, chloro, fluoro, bromo, iodo. So make sure you just recall that. It's pretty straightforward, I think. You know this already. Just remember these names. So you're in business. This is on page 283. My clumsy knuckle hit the off button. So. All right. See where it says fluoro, bromo, iodo. Memorize those names. And that's the only thing that's going to be different from this test compared to the previous test. Now, besides having methyl groups or ethyl groups or propyl groups hanging out from the main chain, you're going to have a halogen. Okay? And make sure when you do the numbering that basically the trick is whatever you have, whatever end of the molecule has more groups, that's what you want to start as carbon number 1. So if you have something like this, if you have, let's see, 1, 2, 3, 4, 5, 6, 7, if you have say a bromine here, and this, and then bromine here. Well, you have more groups on the left side, see? So you want to call this carbon 1, this carbon 2, 3, 4, 5, 6, 7, 8. That way you'll get the lower numbers. So if you have groups piled up on, say, the left side, that's the side you want to start the numbers on. So this would be, bromo position 2, right? And then 2 ethyl, 2, I can't count, 2 bromo, 3 ethyl, 7 methyl octane. Okay. Because you have bromo, and ethyl, and methyl. On the other hand, if you see something like this, if you have a bromine here, and say an ethyl group here, and the ethyl group out here. So if you have more groups on the right side, and name it this carbon number 1, this carbon number 2, 3, 4, 5, 6, 7, 8. Okay, so just this is the trick, because you're going to get the lowest numbers in the name. So whatever end of the molecule has more groups, that's the end you generally want to start at. Yes?
So with the halogens, it's going to stay the same with the alphabetic order?
Yeah, same thing, yeah. So, and I'm not going to take off because you don't have an alphabetical, but strictly speaking, they're likely to put it in alphabetical order.
All
right. The more important is the numbers. If you get the wrong numbers, then you can actually come up with the wrong compound. If you say bromo and then methyl, and then someone else says methyl and then bromo, well, you still know that you have a methyl group and a bromo group. You just name them in not the best order. But if you say 2 bromo, and then someone else calls another that same compound 3 bromo, then there's some confusion as to where that book is located. So the numbers are very important. And also, there's nothing special about a ring. Remember that. You don't have to start at the top, wherever that might be. You just start anywhere you want to so that you get the lowest numbers in the name. And if you have a carbon in a ring that has 2 groups, that's where you want to start. See? So you can call this carbon 1, this carbon 2, this carbon 3. That way you'll have a 1, 1, and a 3 in the name. You don't want to call this carbon 1, 2, 3, so you have a 1, 3, 3. And lots of people want to start at the top and count. You know, there's nothing special at the top. Start where you have two groups, and then you can continue. Obviously, if you have two groups on either side, it's not going to make a whole lot of difference. So you can start. You have a choice. You're going to get a 1, 1, and a 3, 3 in the name, no matter how you number it. All right. So anyway, that's the numberings get to be confusing. Now, be able to do it this way too. If I give you a name, you give me a structure. So here I'm giving you the structure and asking you a name, but be able to do it where I give you a name and say, what is the structure of this compound? So do that both ways. All right. Now, there's also a lot of questions that deal with delta H and activation energies, intermediates, slow steps, and fast steps. So, equilibrium constant. So suppose you see something like this. Let me exaggerate it even more. This is potential energy. This is progress and reaction. You might see something like this. This called curve A, B, C, and D. All right, so I'll give you some curves like this. And I might ask you which one of these reactions is endothermic reaction. A, B, C, D, C. Reaction endothermic. It's absorbing energy. The products have more energy than the starting material. B.
A, B, no.
B. Yes. I should probably label this a bit better. This is potential energy here. So the potential energy is low here, high here, so it's increased. And this is progress of reaction. So the starting material, this starting material could be, I don't know, ABC, X plus Y, Z. So the starting material is X and Y, and the product is Z. So B would be endothermic reaction. It would have a positive delta H, so acid labeled delta H for this. It's this different. This is your delta H. This is positive. You can see where A and D have a negative delta H. A and D, the reaction is exothermic. And which is a two-stepper, that's a gimme. Which one occurs in 2 steps? You have 2 hills, so you know this is a 2-step process. First you form this, you form this. Which one has an intermediate?
D.
This is going to be forming something in this first step, and then the second step is this. Of these 2 steps, which is the slow step, the first or the second?
Second step.
This has a low activation, this is a high. The higher the hill, the slower the reaction goes. So this would be a 2-step. First step is fast, second step is slow. Which one of these, let's just do A, B, or C. Okay, this guy for now. A, B, which one would have an equilibrium constant that's large? KEQ. Equilibrium constant is at equilibrium, you have concentration of products on the top, concentration of reactants on the bottom. So if you have a high concentration of products at the end, very little concentration of starting material, K, capital K, will be a large number. So which one would that give you? see A has lower energy. Low energy is favored. You always favor low energy. So this is much lower in energy. This the products are favored. K, EQ, KC, equilibrium constant will be a large number. Here will be a small number because you're not going to form a whole lot of products. In nature, minimum energy is favored. Low energy is favored.
A would have to greater than 1. There's a font factor that says the KEQ is greater than 1.
Yeah, so a large, by large, it mean a number bigger than 1. So this would be bigger than 1, this would be smaller 1, this would be about 1, because the energy to starting material and product are the same, so you'd have about a 50-50 mixture of starting material and product. So the ratio of products over starting material would be about 1. Now remember where the transition state is located, top of the hill. See? So for reaction A, here's the transition state, B, here it is, and C. All right. And you can only imagine what it looks like. You can't isolate the top of the hill. It doesn't hang out there. It goes there and it falls back down, or it goes there and goes forward. Which one of these reactions, A, B, C, would the transition state look like the products? Transition state looks like whatever it's closest in energy to, and so you're right. B, the energy in transition state is here, and energy in the products is here. This energy isn't that different. Here it's real different. So from curve B, you would predict that the transition state, it looks more like the products. Okay. Transition state, it's a blend. It looks a little bit like starting material, a little bit like the products. But for exothermic reactions, or endothermic reactions like B, it's closer in energy to this product, so the transition state looks more like the products. And obviously, if I ask you which transition state looks more like the reactants, you think A, because this energy difference is smaller, this energy difference is larger. And so for exothermic reactions, it's believed that the transition state resembles the starting material more than the products.
For D, is there 2 transition states?
Yes, there's the transition state for the first step, and then the transition state for the second step. Oh, yeah, transition state. Yes, they're up. Okay, so label delta H. Tell me if it's positive or negative, exothermic or endothermic. Tell me if you have a 2-step process, which is a fast step, which is a slow step. Intermediates. What else am I missing? Can't think of anything else. But anyway, those are the kind of factors you want to be aware of.
For the test, are we going to do like the homework and calculate the kilojoules?
No calculation on delta H's or delta G's. There is one calculation. I'm glad you mentioned that. You will see one calculation on the test. I might ask you to calculate delta H, and it's using kilojoules for a reaction. I would ask you to do that. Let's take this reaction here. Let's take bromine and hydrogen gives me HBO. Okay. Now, of course, for this reaction to take place, you got to break this bond, and you got to break this bond, and you got to form 2 of these bonds. And remember, anytime you break a bond, you have to put energy into the system to break a bond. So give it a plus sign. Give it a plus sign. It takes energy to break bonds. Anytime bonds are formed, energy is released. So give this a minus sign. Give this a minus sign. So basically, these problems, you look up what's called a bond dissociation energies. The energy needed to break bonds. That's what they give you. But remember, when a chemical reaction takes place, you do break bonds, but you also form bonds. So don't forget the sign conventions. And so if you see an equation like that, I will, of course, give you the data. And the data is the energy required to break 1 mole of a type of bond. So you have to consider in the balanced equation how many moles are involved. So this table on page 235, I'll give you part of the table you need. So copy these numbers. CB, BB, let's use the first number, that's kilojoules per mole, that's what chemists like to use. So, I'm not gonna give you this whole table, probably just give you the image. So, it says 192, that's how much energy needed to break these bonds, and that's what we're gonna do in this reaction. So give it a plus, 192 kilojoules. And then, the other bond you wanna break is HH. So, you'll be given the energy needed to break HH bonds, and there it is in the top left, 435. So give that a plus sign. And then you're going to form bonds. When you form bonds, energy is released. So give yourself a minus sign. We're forming HBr bonds. So here it is, 368. Give it a minus sign. But remember, there's two of these bonds you're forming. You get a minus 368 twice. So now, all you gotta do is take your calculator and combine these four numbers. And that will give you delta H for the entire reaction. Okay? So that's the only calculation you'll have to do. Maybe one similar to that. Now, besides all that in this chapter, there are four common, sometimes they call dance moves that you want to be aware of. They're summarized in the back. And just, practice looking at that and being able to perform those moves. Anytime I ask you for a mechanism, remember, this is on page 272, I'm going to give you the starting material and the product. And I'll ask you, how did you go from left to right? Okay? So far, there's a few other ones, not many more. These are the four main mechanistic steps that you want to be familiar with. And always remember, electrons are what move in mechanisms. Arrows originate from electrons. So I know it's tempting, we're here. We should give you the other products here. Let me draw it in. Let's see, this gives you this plus. So I know it's tempting, you see this picture and this. I'm not going to have it over the arrow. I'll have this and this with an arrow, give me this and this. And when you see this and this, and you look over to the right side of the arrow, you see this and this, you say, well, let's see, this has two hydrogens, this has three, so I'm going to draw an arrow from this to this. But see, the hydrogen doesn't move. The hydrogen's too heavy, so to speak, compared to the electrons. Remember, you need about 2,000 electrons to equal a mass of a single proton. So the electrons are really kind of mobile. They kind of move around and grab things. So it's not considered correct to take an arrow and put this over here. It doesn't happen that way. Instead, these pair of electrons go and attack that and grab it to form a bond, and then this pair of electrons moves back in. Notice we start with a positive and neutral. We end up with a positive and neutral. Okay, so that's a proton transfer. And don't take that shortcut. Don't just draw one arrow. You gotta have two arrows. Don't have an arrow from here to here. Okay, you'll get partial credit, but that's not the whole story. Anyway, this is a rearrangement. That's one. This is loss of leaving group, and then that's a nucleophilic attack. You can't see very well. Okay, so those are the four movements. And any mechanism I ask you will be one or more of those movements involved in the mechanism, okay? So be able to do those. And again, anytime I ask you for a mechanism, I give you the starting material, I give you the products, and I tell you how, ask you how you get there. Now, there's only two mechanisms you gotta learn. And one is the SN2, the other is the SN1, okay? So let me give you one, see if you can tell me. The easiest one is the SN2, don't miss this one. That's the beginning. The hard one is the SN1. So if you see something like this, mechanism. This is two of those movements. It is nucleophilic attack and loss of leaving group. Okay, so those are the two things you see: nucleophilic attack, and loss of leaving group, and they could occur simultaneously in a single step. Two things are involved in a single step mechanism. That's why it's called SN2. It's a substitution. It involves a nucleophile, and it occurs in a single step. And two things are involved in a slow step. See, the rate of this reaction is an SN2. The rate depends on the K times the concentration of the nucleophile times the concentration of the substrate, which I used to call RBR. Okay? So if I double either one, then I know rate. So for this mechanism, I'm going to look for 2 arrows. This attack, okay, and this lead. So you have attack, nucleophilic attack, and loss of leaving all at the same time. No, I'm going to say, here's a rate. Well, you got to know, if I say the mechanism is SN2, you need to know it depends on the concentration of two things, the nucleophile and the, what they call the substrates.
What does it say? It says K and then OH, R, on it.
Yeah, this R means the rest of the molecule. So in this case, R is this piece here. Chemists have gotten lazy, or this piece here. So if I have one carbon, this is, or if I have 2 carbons, these reactions all take place, they're all the same, all these undergo the same type of reaction. So a general way of writing this is simply RBR. R just means the hydrocarbon portion of the molecule, the rest of the molecule. In organic chemistry, that's the terminology they use. So specific, strictly speaking, you should write, I guess, CH3BR, but you want to put RBR, that's fine. Now here's something very important you want to remember. Halogens are bad, good leaving groups. Good leaving groups. They don't need any help, okay? OH is a bad leaving group. It needs help big time. It can't leave on its own. It's got to be protein first, okay? So suppose I ask you this mechanism. Let's say that's not going to leave on its own. Let's take bromide. Okay, I'm going to need an acid in order to get the OH to leave. We wouldn't really care about the product. This acid is just a catalyst. It's going to be, using the first step and kind of lost in the second step. We do something for it, we change it so that we can't do that. Okay. If you have a halogen, there's no problem. It just leaves. But if it's an OH, it's not going to leave on its own. It's OH minus is a bad negative, so you got to make it a neutral negative. So you add sulfuric acid that produces hydrogen ions, and so I'm going to look for an equilibrium is established, a rapid equilibrium is set up. They don't even consider that a step, but we will. This will be a two-step process. Just consider the starting materials and the products, and ask yourself, what does this, and this have to do to make this and this? What had to happen? When this left, this is attached to it. This can't leave on its own. So the first thing you want to do, if you want OH to leave, you got to add an acid. That's one way to get it to leave. And so the first step is you protonate the acid. Now again, it's tempting to put an arrow from this guy to this guy. That's what it's tempting to do. Don't do that. Do this. So you protonate the oxygen first. And like I said, they don't really even consider this a step. It's just a rapid reversible equilibrium. Just bounces back and forth. Now that the true reaction takes place. Now this can come in and this can leave. In these products. Because water is a good leaving group. It's neutral. You can have water leave. You can't have hydroxide ion leave. So you might see that mechanism. If it's an OH, there's a pre-step, so to speak. You got to first protonate the oxygen. Then everything else is like before. So one little extra step. And the acid used is sulfuric acid, pretty much. That's usually used. But they're just write H+. Okay, just get rid of the clutter. All right, while we're at it, I'm not going to ask you for this mechanism, okay, because it's messy. But let me just show you there's two ways to get rid of this guy right here, so that it can be substituted. One is to add an acid, okay? There's a second way. Sometimes when you add an acid, you get carbocations, and carbocations tend to rearrange and give you mixtures of products. So if you can avoid a carbocation, don't do so. So just to avoid the possibility of a carbocation forming, carbon plus charge forming, what they'll do, and this mechanism is a bit messy, but what they'll do is something different. And before I do that, let me just tell you something. This reaction we just did, we added an acid, sulfuric acid, and at the same time we dump in sodium bromide. Okay, and we got our product. You just mix everything together. That's all you got to do. Just toss it all together. The methyl alcohol, the sulfuric acid, and the sodium bromide, and out pops the organic product of interest. The other product, which we don't care about, is going to be water, so I'm not going to ask you for that. And the other product, which we don't care about, is going to be sodium bisulfate. But we don't care about those guys. I'm just working with organic product. There's another way to make this a better leaving group. We talked about it last week. Add potassium chloride followed by sodium bromide. Now here's the problem. You can't mix these guys together. So you'll see number 1, number 2, and then you get your product. Okay? So don't be upset if you see 1, 2. It just means that they have to do it in 2 steps. It means the reactants, in this case the potassium chloride and the sodium bromide, they react with themselves, not with the alcohol. So first you add 1, then you add a second. Okay? So sometimes you'll see no numbers, just a bunch of stuff added. That means you just toss everything together at once, it reacts, you get a product. Sometimes you'll see number 1, number 2, and so forth. Okay? Anyway, this is the extent of what I'm going to ask you. This part. Now, we don't care about the other products. Okay? The other products will only be, let's see, HCO and sodium tosylate. Okay? But I'm not going to ask you for the other products. This is the main thing we're looking for. The tosylate is a throwaway. Okay? Now, we did this last week, and I'm sure by now it's happening. Yep, I was making. But basically what happens is, in step number 1, methyl alcohol reacts with tosyl chloride. Tosyl chloride looks like this. And so this comes in, kicks up the chlorine, and then in the next step it loses the hydrogen. And again, I'm not going to ask you for this mechanism, it's just too messy. But this is what happens. This lost the chloride, Cl minus, and then this loses an H. Pair of electrons goes back on here, and these two guys connect, okay? So you end up with HCl. And you get this. This is why I'm asking you for mechanisms. It's too messy. Now, bromide can come in from behind and keep this guy. And use your product. And you get this is called the tosylate ion. Very, very stable because this negative charge doesn't have to sit on just one oxygen. This negative charge can be spread out over three oxygens. It's a good leaving group. See? OH minus is a bad leaving group. If OH minus were asked to leave, the negative charge sits on one atom. An oxygen doesn't mind having a negative charge, but it's not that stable. This is a much better leaving group. So you convert this into this. This is a great leaving group. This is a bad leaving group. Okay? So there's two ways to make this a better leaving group. One way is to add an acid, protonate this, then it leaves. You get substitution. Another way is to add tosyl chloride, make this right here, then it can leave. All right, but you can never just have this leave by itself. Okay? It's got to have some help. Okay? Acid's easier to do, cheaper, but sometimes you get side reactions if you have the acid there. So for that reason, they'll use tosylate. So typical question would be something like this. There's a few reactions you're going to memorize. They're all substitution reactions. Thank goodness. And you give me a product of that reaction. And then you might see something like this. Oops, you got an acid. Have an acid first, okay? Or with that. And so you might see this question written either one of two ways. I'm not going to ask you, a question like this, I'm not asking you for the mechanism. When I ask you for the mechanism, I'll give you the story material and the products, and I'll ask you, how did you get from story material to product? What had to happen? If you see something like this, I just want to know, what do you get if you mix these guys together? What do you get? What's your final product? And all I want is the organic product. You don't need to give me the throwaways, okay? So you don't need to go through all of the detail. I'm not asking you for the mechanism, I just want the product. And this is where organic chemistry is so confusing. There's so many, dozens upon dozens upon dozens of reactions you have to learn. Thank goodness the first test, they're all substitution reactions. So you know, every single reaction I give you is going to be a substitution. But later you're going to have addition reactions, elimination reactions, oxidation reactions, reduction reactions. It just gets to be nuts. But at least this next test, it's only one kind, that's it. And that's going to be substitution. And what's going to get substituted? Either OH or a halogen. That's it. Okay? So that's the leading. So that makes life simple. So in both these cases, I'm going to get substitution. Okay? Now again, I need special resistance. I need this to help get rid of that. I need this to help get rid of that. If I have this, I have a halogen. I don't need anything special. I can just simply add sodium cyanide. Okay, so you see how they differ? Those are pretty much just types of reactions you want to learn for this next test. Substitution, and where some nucleophile is going to substitute for a halogen or an OH. That's it, okay? So enjoy it while you can, because it gets nuts after. Start with the next chapter. Now, in this test, I'm going to give you the starting material, the reagents, and ask you for the products. Okay? This starts off slow, but probably the next test, I'm going to give you the product we wish to make and the reactants that we have available, and ask you, what do I need to start with if I want to make this, and I have these reagents available to me? What do I need to start with? Okay, so not for this first test, but that's something you want to be aware of. And of course, the other variation will be, I'll give you the starting material that I have available and the product that I wish to make, and I'll say, what reagents do I need to convert that to that? Now, that's the most difficult. When I ask you that question, I'm going to give you a list of reagents to pick from. So you won't have to at least memorize all the reagents. So you'll see, pretend you don't see this. Okay, I'll have a list. I'll have sodium cyanide, I'll have H+, I'll have copper chloride. Okay? And then so I'll say, okay, what do I need to add? And so you pick from the list. You say, okay, here's what I have available. I'm going to go from here to here, or from here to here. So you have different options. From here to here, you can just say sodium cyanide. Sodium cyanide. From here to here, you can add this and this. I'm sorry, this followed by this, or you can add these two together. So that's what we're going to build up to slowly. Okay, we'll take it nice and slow. All right, so try to get a good foundation of this, and that way it's bad. All right, what about the SN1 mechanism? Okay, can you do this? Can you show me how, this is the other mechanism, how this happens? What is going on? And let's try to keep like now remember this. If you have a negatively charged nucleophile, it tends to go by the SN2 mechanism, because negatively charged nucleophiles are powerful nucleophiles. They're like bullies. They don't wait for the leaving group to leave. They come in and kick it out. Neutral nucleophiles are more subtle. They wait for the leaving group to leave, then they make their move, okay? All right, and we're gonna get a rearranged product. Notice the leaving group is on the end carbon, but the nucleophile ends up in the middle carbon. So if that happens, you know that carbocation rearranged, okay? So remember the 4 dance moves, okay? You're gonna have loss of leaving group, you're gonna have nucleophilic attack, and then you'll have a proton transfer, okay? So can you come up, actually, I'm sorry, and you get a carbocation rearrangement too, don't you? So let's go back. You're gonna see all 4 steps here. You're gonna have loss of leaving group. You could have, then after that, you could have rearrangement, carbocation rearrangement. Then you're gonna have nucleophilic attack, and then you'll have proton transfer. So all 4 steps are required for this reaction to take place. Slow step is always a formation of carbocation. I'm not going to ask you which is a slow step. Just give me the 4 moves that allow you to go from the start material to the product. And I guess I should write the other product for you. HBr. All right, so this is hard. This one's more challenging. Okay, but you're going to see something like this. If I say SN1, you know a carbocation is formed. See, that's the mechanism. So this leaves in the first step. When you get this, and Br minus, which we'll probably get from now. All right, now this is the first main carbocation, right? If you can rearrange it to form more stably, carbocation will do so. So this hydrogen will slide over. This is the first step. This will be the second step. That hydrogen slid over. So that's carbocation rearrangement. Now, okay. So this attacks this carbon, should have been positive charge underneath, okay? And so after that attack takes place, you get this. And finally, here's the only Br minus, we can pick on that guy, and this carbon electrons in that here. Chemists love mechanisms of organic chemistry. So 1 arrow in the first step, 1 arrow in the second step, 1 arrow in the third step, and 2 arrows. Proton transfer always involves 2 arrows. Okay. All right, so that's messy. There's no way around it. You have to do that. Understand how to do that mechanism. I like the SN2 because it's just a single step. 2 arrows, 1 step, but this is messy. So, you know, practice, practice, practice. I'm going to give you a very simple molecule, nothing fancy, and if you can do this, then you're in good shape. Okay, and finally, make sure you know the characteristics of SN1 and SN2 reaction. We're not going to talk about polarity effects, I know I did, but it's just too confusing. So, for instance, let me list some things I can think of. Characteristics of SN1 and SN2. We have SN2, it's second order kinetics, in other words, the rate depends on the concentration changing the concentration of nucleophile is not going to make any difference in the speed of this reaction. Only the subject. Because the slow step one involves this. But for SN2, changing the concentration either of the nucleophile or of the substrate makes a difference. Another difference is usually use a strong nucleophile. Not always, but usually it's negatively charged. Okay, it's a bully. This goes in and pushes out the lead group. SN1, you usually tend to have a weak nucleophile. Nucleophile still has a lone pair, but it's not negatively charged. That favors. SN2, you get no rearrangement. So I'm asking all these, because you don't get a carbocation like we do with the SN1. See the SN1 mechanism, you get a carbocation and you get rearrangement. So with the SN1, you can say the rearrangement is possible. Okay. Now, with the SN2 mechanism operating, you get inversion of configuration. The molecule basically gets turned inside out. And you get no loss of optical activity. If your starting material is optically active, your product will be optically active. Just turn inside out. That's because the attack can only come from one side. It can't come from both sides. And it comes only from the back side. Whereas if you have SN1 mechanism operating, you get a mixture. You don't get inversion, you get a mixture. And if you start with optically active material, you lose optical activity. If your starting material is optically active, your product will not be. And the reason is, just in a nutshell, my models here, but let's say, let's pretend this is an optically active compound. I have 4 groups attached. Okay. 4 groups. And if it's SN, let's say this is the leaving group here. If it's SN2, this guy comes in from behind. It doesn't come in from this side. This is the leaving group right here. Okay. It's going to come in only from this side, push this out, and invert everything. See? So you don't lose any optical activity if the mechanism is SN2. Okay? But if it's SN1, and this is optically active, let's pretend this is optically active, just say it's 4 different groups. What happens first is this leaves. Oh, that's not the leaving group. This leaves. And this turns flat, perfectly flat. Now the nucleophile can come in from this side or this side. You get a 50-50 mixture, so you lose optical activity if the mechanism is going to be SN1. If you start with something that's optically active, you're going to lose it. Okay. So those are characteristics, those traits led chemists to come up with a mechanism called the SN1. If they found this was true, and this is true, and this, and this, and this, they said, well, here's an explanation for these facts. This is the mechanism. And then other times they do a reaction, they get these things taking place. And they say, well, let's come up with a story or a mechanism to explain these facts. So all of these mechanisms are just theories used to explain facts. Yes?
I'm sorry, what does it mean to be optically active?
It means it rotates light to the left or to the right. I don't have my models with me, but I mean you have 4 different groups of tetracarbon. And you only have 1 of 2 possible mirror images. See, so if I have 2 hands together here, this, with one hand rotates light to the right and the other rotates light to the left. If I have them both together, you don't get any rotation. But if I have just one hand, say my left hand, and it rotates light to the left, 1 of 2 possible enantiomers, if just one is present, it will be optically active. If you have both of them present, then you don't have any optical activity. Now, there's one more criterion which I forgot. Let's go back to the SN1 mechanism. Stirred constraints aren't important. Okay, so I have 4 different groups that say, this is the leaving group, it leaves, I form a flat carbocation, and I don't have any worries about steric constraints, okay? I don't have steric or crowding issues, okay? But if I have the SN2 mechanism, what happens is, let's say this is the leaving group, this has to come in from the opposite side, push this guy out, and so in the transition state, you got 5 groups, this coming in, this leaving, 5 groups, so crowding is an issue with the SN2 mechanism. So for that reason, reactivity follows this pattern. Remember this. If you have a carbon with a leaving group, let's say a halogen, and you have 3 carbons attached to this is a 3rd degree alkyl halide. If you have a carbon with a halogen, and you have 2 carbons attached to it, and a hydrogen, this is a 2nd degree. If you have a carbon with a halogen, and you have 1 carbon attached to it only, this is a 1st degree. And then if you have carbon with a halogen, and you don't have any hydrogen, any carbon, this is a methyl. So if you have a group coming in from behind, a nucleophile coming in from behind, you're going to have some crowding issues here, 3rd degree. You're not going to have any crowding issues for methyl. So the reactivity for SN2, this reacts the fastest and this reacts the slowest. So let's add to this list of characteristics of SN2. The reactivity follows this pattern. Methyl halides react the fastest, followed by 1st degree, followed by 2nd degree, followed by 3rd degree. So that will be a pattern if the mechanism is SN2. Now what about if it's SN1? Well, if it's SN1, this doesn't attack. First, this leaves. Okay. So if SN1, this leaves, you get a 3rd degree carbocation, which is stable. If it's the methyl halide that's reacting and this leaves, you get a methyl carbocation. And the more carbons you have attached to this carbon, the more stable it is. These carbons push electrons into this carbon, minimize this positive charge. Hydrogen can't do that. So sterility, 3rd degree alkyl halides form 3rd degree carbocations, very stable. Methyl alkyl halides form methyl carbocations, which are extremely unstable. So because SN1 involves formation of carbocation in the slow step, the reactivity is reversed. 3rd degrees react the fastest by the SN1 mechanism, followed by 2nd degree, followed by primary, and you will never get the SN1 mechanism operating because of methyl halide. It just won't work. Okay? So do you see how the reactivity is different? So all of these characteristics you want to make sure you know. Okay? You don't need to memorize it as much as you got to, if I say, which mechanism gives you no loss of optical activity? So then you'll say it's SN2. Okay? You don't have to memorize these things, just understand that which gives you inversion, you'll say SN2. So it's going to be a 50-50 guess. I'll have a bunch of questions, and I'll say, which one of these do you get inversion of configuration? The SN1 mechanism or the SN2? So you say SN2. Which one of these mechanisms will you lose optical activity? And again, the answer is going to be either SN1 or SN2, so hopefully you'll pick SN1. So just understand these characteristics, and you'll be in good shape. The other thing I'll do, I'll give you these guys here. And these four, see these four compounds? I'll say circle the one that would react the fastest by the SN2 mechanism. Which will react the fastest by the SN2? So hopefully you'll circle this one. And or I might say which one reacts the fastest by the SN1 mechanism. And hopefully you'll pick this one. Okay, so just be able to do that. No solvent effects, so it's just too messy. We're not going to do solvent effects. All right, so that's, that's it in a nutshell. Now, what's coming down the pipe, not so much in this, I haven't made a test yet, but I don't think I'm going to put it in this test. I don't know, I might. But you're going to practice your artwork, okay? Just so that you can grade these things. We're going to stomp on these 6-membered rings.